Hey guys, this is Akansha and welcome to Tech Master Ani. In our previous session, I have covered some of the basics of diffusion process. In our today's session, we will understand what all are the diffusion type we use in our fabrication process. So let's start today's session. So we have two types of diffusion process. First one is a predeposition and second is a drive-in. Predeposition is also known as infinite source diffusion and drive-in is also known as limited source diffusion. So now let us understand first our predeposition process. As the name suggested, it has an infinite source diffusion. So the source of dopant is present as long as we want. There is a no scarcity of the dopant. So that is why we call it as infinite source diffusion. Now let us understand its fabric process. So we have our p type of substrate. So it is a uniformly doped p type of substrate having concentration of acceptor Na. Now we will grow a oxide layer by using oxidation process, whether it can be wet oxidation or dry oxidation. Then we will use our lithography for opening this particular window. So this much we have already covered in our previous session. Now let us see how we will insert our dopant into this particular region. So we have our infinite source of phosphorus. This is my infinite source of phosphorus. It will present as long as I want. So under the 1000 degrees centigrade, we will diffuse this particular dopant into our p-type of substrate. As we know, our diffusion process will happen from the higher concentration to lower concentration. So when this particular dopant of Nd, which is a phosphorus, or you can also say it as donor, will go to the surface of the p-type of substrate, it will dissolve in this particular substrate, in the upper part of this particular substrate. So this is my surface and here is my source of Nd. So when it will diffuse to this particular area, it will dissolve in this surface. So the amount of donor which will dissolve is known as solid solubility. So it is known as solid solubility. The number of dopant which can be dissolved by this particular surface is known as solid solubility. Okay, so now let us see, after diffusion of this particular Nd in the above surface, which is x is equals to 0, you can say this particular portion as x is equals to 0 as x is increasing in this particular direction. So at x is equals to 0, your concentration will be solid solubility, and if you will increase the temperature to 1000 degrees centigrade, then there will be a diffusion process. Under diffusion process, the concentration from the higher, it will go to lower. So now it will diffuse to the lower part of the substrate. In this way, my my dopant will present all over the surface. But my source is present for the infinite amount of time. To stop the diffusion, I need to decrease my temperature. If I will decrease my temperature to 800 degrees centigrade, it will stop my diffusion process. So this is what happened in predeposition. I hope you have understood this particular point. This is nothing but we have our donor and it will diffuse to the surface, which is x is equals to 0, which is the upper surface, and the amount of dopant which will present in the upper surface is equals to solid solubility of the substrate, and after that there is a diffusion from the higher concentration to lower concentration, so the dopant will flow into the substrate, and to stop the diffusion process I have to decrease my temperature so that it will stop the process of diffusion. So this is all about the predeposition. I hope you have understood this particular point. Now let us understand the parameter of diffusion. So first parameter is the surface concentration. Just now I have told you the amount of dopant which will reach to the upper surface is called surface concentration. It is equal to solid solubility of the substrate. Okay, it is a function of temperature and always constant. So it will be always constant. It means the amount of dopant which will enter to the surface is equal to amount of dopant which will diffuse to lower part. It's simple. If four atoms will reach to the surface, then four atom which is already present here will diffuse to the lower part of my substrate. In this way, the concentration at x is equals to 0 will always be constant. Hope you have understood this particular point. Vacancy created at surface is constant. It means the same. The amount of dopant will be constant in the substrate. So this is all about the surface concentration. Now next important point is a doping profile. So which kind of doping profile will created after the predeposition? So let us understand here. Previously I have my p-type of substrate. So having a p-type of substrate, it means I have only acceptor concentration which is uniform in nature. So in all over the substrate I have Na which is uniform. But what happened after the predeposition? Let us see here, we have our N type of dopant. Let us see the concentration of N type of dopant here. So the N type of dopant will be maximum in the surface. You can see here, and as you will go to the X direction, the concentration will decrease. So in this way, you will get this kind of profile which is known as complementary error function, ERFC, known as complementary error function. So by the predeposition type of diffusion, you will get complementary error function. So in the previous session I have told you this second order differential equation. After solving this second order differential equation, we will get the function of concentration. To solve this particular equation, we will use a boundary condition. Let us see here boundary condition first. So here in a boundary condition at x is equals to infinity, it means from the very last corner of my surface substrate, my concentration will be 0. Obviously it can't reach to the this particular last point to my substrate, so it will be 0 there. And the second point is surface concentration at x is equals to 0. So I know surface concentration at x is equals to 0 is my solid solubility, which is highest, which is known as Ns. Okay, so it is highest here. You can see it. This is highest here. And the third point is at t is equals to 0. It means at time is equals to 0, there will be no concentration. Obviously, at time is equals to 0, there will be no concentration. So using these three boundary condition, we can solve this particular second order differential equation. After solving it, we will get this expression. So this is the expression of the concentration of my dopant into the substrate, which is equals to Ns ERFC x upon 2 root over dt. Let us understand one by one. This Ns is a surface concentration, which is solid solubility, which is the concentration at x is equals to 0. I've told you. The second is x. X is the distance. As you go inside the surface, it is the distance. Okay. Then this d is diffusion constant and this t is a time. So this is all about this particular expression. So this expression is very, very, very important for the prelims point of view and hell important for the mains point of view. Direct question can come into this particular expression. So I think you have understood this point clearly. Now let us understand junction depth. So we had our uniformly doped Na, and now we have created N type of dopant layer. So you can see here, or here I can create, the concentration will be highest in the surface and it will go lower. This concentration is highest Ns and it will be lower down as we go to the X direction. So this is the thing we have told you about. So now let us see what happens when there is a junction formation. Obviously there is a junction formation. This is my P region, this is my N region, and between this P and N we have our depletion region. So what happened here? At the X is equals to 0 point, it means the above upper layer we have highest concentration of my dopant, and as I go to the X direction my dopant level will decrease, and there will be a point when my dopant concentration will be equal to my acceptor p-type concentration. So this particular point is known as junction depth. So in the junction depth, the concentration of the dopant and the concentration of acceptor will be equal. So that is why there is a junction formation. And after that junction point, my acceptor concentration will dominate and it will be more than the depletion region, dopant concentration. So that is why after this particular junction Xj, this particular area is my P type of substrate or my substrate, and before this junction I have my dopant Nd present, and at this particular junction point my Nd is equals to Na. So this is all about the junction depth. So you have understood this particular point, that at junction depth my concentration of dopant will be equal to concentration of acceptor. So this, by using this particular point, I can evaluate my junction depth. So let us see here. In the previous we have seen this particular formula. This is a formula of Nd, or you can say this is a formula of concentration of dopant. So if I will equate Nxt is equals to Nd, I will get the depth of my junction. So it is a simple process. Equate my concentration equal to Na. Na is a concentration of P type of substrate. So I can evaluate my Xj. I hope you have understood this particular point here. So in the next session, we will see some of the problems. So you will get a better understanding how to calculate this particular junction depth. As of now, I hope you have understood this particular point. Now let